Hello and welcome back to Little More Learning. Today we are going to discuss about diagonalization. So, diagonalization is a crucial concept in linear algebra that simplifies matrix computations, making it essential for machine learning, data science, and artificial intelligence. So, what actually is diagonalization? So, it is a process of converting a square matrix A into a diagonal matrix D using a similarity transformation. The equation is A equals P, D, P inverse. So where A is the original matrix of size n cross n because it is a square matrix. P is an invertible matrix, D is the diagonal matrix, and P is the inverse of the matrix P. So why diagonalization is important? Diagonal matrices are much easier to work with than general matrices because firstly, matrix exponentiation is simple. Computing powers of a diagonal matrix is straightforward. Next is solving linear systems become easier. How come? When a matrix is diagonalized, systems of equations can be solved efficiently. It is useful in machine learning and AI. Many algorithms rely on spectral decomposition and eigenvalues, which require diagonalization. So next is, when can a matrix be diagonalized? So matrix A can be diagonalized if it has n linearly independent eigenvectors. Now, what does that mean? Firstly, the matrix must be square. That is, it should be an n cross n matrix. Secondly, the matrix must have n distinct or linearly independent eigenvectors. N linearly independent eigenvectors. If a matrix has n distinct eigenvalues, it is always diagonalizable. So when you are diagonalizing a matrix, the first two things that you require are eigenvalues and eigenvectors. If you don't know what they are, you can just move towards the video that concentrates on eigenvalues and eigenvectors, how to calculate them using a simple matrix example also. So just a brief to them. So let's talk about here eigenvalues. So an eigenvalue lambda of a matrix A satisfies the equation A minus lambda I V equals 0, where A is our given matrix, I is the identity matrix, lambda is an eigenvalue, and V is the corresponding eigenvector. And now when we talk about eigenvectors, eigenvector V satisfies the equation AV equals lambda V. They are special vectors that remain in the same direction after linear transformation. How to diagonalize a matrix? We will move step by step. Step 1 is to calculate eigenvalues. Find the eigenvalues lambda by solving the characteristic equation. So our characteristic equation of finding the determinant of A minus lambda I. Then step 2 involves calculating the eigenvector. For each eigenvalue lambda, we need to solve the equation A minus lambda I equals 0 to find their corresponding eigenvector V. Step number 3, it is to form the matrix P and its inverse. So what we need to do? Firstly, construct P. How we will construct P? Using eigenvectors as columns. And after that, we will get the matrix P. And when we have P, we can calculate P inverse from it. Step number 4 is to calculate the diagonal matrix D. So D is a diagonal matrix with eigenvalues on the diagonal. So what our matrix D will look like? So D equals lambda 1, lambda 2, lambda 3, and rest of the elements of this matrix will be 0. So this will be our diagonal matrix. The last step is to verify the similarity transformation. What here we will do, the equation that we just learned in the starting, we will put the values into this and verify that the answer of majorly this equation is equal to our original matrix A. So these are the steps that we will follow to diagonalize a matrix. So let's take a simple example of a matrix A that has the components this. So first step is to find the eigenvalues. So we will be solving for determinant of A minus lambda I equals 0. So for this, we will get this as the matrix. And on expanding these and solving this matrix for determinant, we will get this quadratic equation. And I'm solving this particular equation simply using the substitution method. You will get the eigenvalue, that is lambda 1 as 3 and lambda 2 as 2. The next step is to find the eigenvector for our first lambda, that is 3. So for this, we will put it into the equation. This is what we will get on solving. You can just refer to the eigenvector video and you will get to know how I am doing this. And the output will be 2, 1. Similarly, when you will solve for the second eigenvalue, that is 2, you will get V2 as 1, 1. Same methodology to be used into this vector to get the output. Step number 3 is to form the matrix. So P will be 2, 1, 1 and 1, and D will be 3, 2, because these are our 2 eigenvalues and rest elements are 0. And inverse of P will be 1 minus 1 minus 1, 2. Now, lastly, what you will do, you will check on to this equation for the similarity transformation. So lastly, we will talk about applications of diagonalization in data science, machine learning and AI. They are firstly in PCA. So PCA relies on diagonalization to reduce dimensions and remove redundancy. Eigenvalues represent the importance of each principal component. Next is machine learning models. Linear regression and clustering algorithms use diagonalization for feature selection. Next, you can find the application in neural networks. Optimization algorithms in deep learning rely on eigenvalue decomposition. Lastly is quantum computing and AI. Here in quantum mechanics, Hamiltonian matrices are diagonalized to analyze systems. So lastly, diagonalization is a powerful mathematical technique that simplifies complex transformations, making machine learning algorithms faster and more interpretable. It plays a significant role in PCA, optimization, feature engineering, and deep learning. So that's it for the topic diagonalization. And if you like the video, please give it a like and subscribe to the channel. And see you in the next one. Till then, happy learning.